Hello everyone, your pal 6Speed here, and due to the tremendous response to my last lecture video on evaporative emission systems, I've decided to do another one, and today we are going to be talking about ignition systems. So, we're going to start by answering the question, what is an ignition system? Basically, a gas engine, a gasoline engine, a natural gas engine, or a propane engine requires a spark to ignite the air and fuel mixture in the combustion chamber at a precise time. The ignition system provides the spark at that precise time, but it also provides, again, the precise timing and also the ability to change the timing dependent on engine RPM and loading. We'll get to that later on in the lecture. So, the heart and soul of any ignition system is the ignition coil. Now, some cars have multiple ignition coils, some have one. It all depends on the style of ignition system that you have. We will get to that a little bit later on. But basically, we're going to go over how an ignition coil functions. So, an ignition coil works on the principle of Faraday's law of magnetic induction. So, basically, the principle in a nutshell is when the magnetic field cuts across a coil of wires, it induces an electromotive force, or a voltage, in the winding. Now, as you can see by my crudely drawn drawing here, we're just going to have to use our imagination and assume that both the primary and the secondary are wound about the iron core. The reason that they use an iron core is because iron is magnetic, and the iron itself will actually strengthen the magnetic field produced by the primary. Now, notice that the primary has a lot fewer coils of wire than the secondary, and this is due to the coil basically being a step-up transformer. So we got a lot of coils in the secondary, very few coils in the primary, so that increases our voltage but lowers our current at the same time. The voltage and the current on a transformer works inversely proportional to each other. So, here's the nuts and bolts of how an ignition coil works. So when we supply a power source to the primary side of the ignition coil, i.e. battery voltage, it creates a magnetic field. The magnetic field will generate from the primary winding around the iron core. Once we remove our power source, the magnetic field will collapse. And it collapses very rapidly. And when it does so, it cuts across the wiring of the secondary winding. And it induces a very high voltage, basically, is created in the secondary winding. And that's where the spark in the ignition system comes from. So, now that we've kind of discussed the heart and soul of every ignition system basically ever made, we're going to talk about one of the older types of ignition called the distributor type ignition. Now, this is even still produced today. The picture that you're seeing is a newer style MSD ignition. It's an aftermarket distributor, generally for hot rodders and stuff like that. People that like to go fast and build old school stuff. Companies like Mercury Marine will still produce the old GM small block that has a distributed ignition, so on and so forth. So distributors haven't completely gone the way of the dodo, but you're not going to see them in a newer car anytime soon. So this diagram here is basically the distributor in a very simplified look. So, as you can see by my mouse cursor here, we have the ignition switch, which supplies the power to the primary side of the ignition coil. And then we have the trigger, which is able to control when the ignition coil, the power to the ignition coil is cut. So instead of removing the power source, it actually cuts the ground source from the ignition coil. And that's what causes the ignition coil to fire. So you can see the ignition coil is routed to the center point of the distributor, which basically sends a voltage onto the rotor. Now, depending on what terminal the rotor is pointing to, it will send a spark to that specific cylinder. The distributor cap has the different terminals in it, including the center terminal for the ignition coil. And the spark plug wire, which is connected to all the side terminals, connects to the spark plug, which is screwed down inside the cylinder head. Again, basic engine operation. So the distributor, very simple, not all that complicated, is reliable for the most part, and it actually provides adjustment for tuning. You can rotate the distributor one way or another by loosening the hold-down clamp. That provides a little bit of adjustment for tuning. Newer cars with distributors, usually kind of ended in the late 90s, early 2000s, but the newer cars don't necessarily provide this adjustment. But old school small block Chevys, they definitely did. But the only issue is there's a lot of moving parts that wear out. The cap, the rotor wear out, stuff like that. Spark plug wires, and Lord knows spark plug wires are not cheap. The only problem with this is it doesn't deliver as high of a voltage output as other ignition systems. So this is basically a distributor without a cap and a rotor on it. So we have the drive gear, which in this case, this is probably off of some kind of small block Ford, Chevy, or Mopar. So the drive gear is driven actually off the cam gear in this case. It's usually driven off of the camshaft of an engine, not the crankshaft, as it's timed with the firing of the cylinders, which is kind of what the camshaft does. I got a separate lecture on that coming up. The body of the distributor, which is usually in this case, it's billet aluminum, kind of provides a area for the shaft to ride on. So we have the trigger, which controls when the ignition fires. We have our ignition module, which translates that signal from the trigger into a usable signal for the coil. And we have our centrifugal advance. Now, we'll go into this a little later, but this allows us to actually gain more timing advance as the engine RPM increases. And this is our vacuum advance, which provides more advance under part throttle operation. Again, we'll get to that a little later on. And so, again, so this is the distributor cap. That's kind of, again, it's kind of an essential part of this. That's kind of what points all the, that's what it has all the different terminals in. It's what allows the spark plug wires to be put on at different points, just for your engine firing order. And our rotor, which distributes the spark to all the different terminals inside the distributor cap. So this is a picture of the underside of the distributor cap. As you can see, the center button right here is where the ignition coil goes onto, and when the rotor points to each one of these terminals and the coil fires, the spark will travel from the center button up through the rotor, and it'll jump to one of the terminals. So you can see this distributor cap has seen some better days. This one's seen some action, but that's basically how a distributor works. As the rotor is pointing to each terminal, the trigger will fire the coil, and the rotor will send the spark up through the metal contacts of the rotor into the contact point on the distributor, up through the spark plug wire into the spark plug. So we have a couple of different types of trigger. We have our points and condenser, which is a manual trigger or mechanical trigger. We have our electronic triggers, which the three big ones are a magnetic trigger, a Hall effect trigger, and an optical trigger. So, kind of again, starting with the old school here, this is a points and condenser type ignition system. This is kind of the earliest. Again, not quite. Well, these have completely gone the way of the dodo as production standpoint, but I have run into actually quite a few of them. You'd be quite surprised. Generally in marine applications, for some reason, they were used up until later years. So we have our cam, which is attached to the rotor shaft. We have our breaker points, which ride on the cam, and the cam pushes the breaker points open and closed. We have our condenser, which we'll get into the operation of that, but that's a very essential part of this system. And our points are basically connected directly to the ignition coil as they ground out the coil and allow the ignition to fire. So points of condenser, they are simple and relatively inexpensive. The only problem is they wear out very quickly, and they do require constant replacement and adjustment. So when the points wear out, the point gap increases. Now the point gap is the distance between the contacts of the points when they're fully open. And when this happens, the charge time on the coil decreases, and that results in a weaker spark. So this is basically how a point system works, according to my crude drawing. So we have positive power from the ignition switch. on the one side of the primary of the coil, and on the other side of the primary side of the coil, so basically we have a positive and negative side of the primary of the coil, it goes out to the points, and the condenser is kind of wired in parallel here. So when the points close, we have current flowing through the primary windings, which charges the coil. When we open the points, that sends a high voltage discharge to the secondary of the coil, basically to your distributor. And what happens when the magnetic field cuts across the primary of the coil is it will tend to induce a voltage into the primary of the coil. And the point of the condenser is to absorb that just because of the self-induction that occurs. And what that does is that prevents arcing across the points. Without the condenser, if you have a failed condenser, you'll notice very quickly that your points are all burned up and toast. They won't last very long. So point gap. It's very critical for the correct operation of your ignition system if you have a points and condenser style ignition. It's set when the points are fully open using a feeler gauge. If it's too tight, the dwell time, which is the time that the coil is energized, is very long. If it's too loose, or the point gap is too large, the coil doesn't charge long enough, resulting in a weak spark. So, the dwell angle. This is another way of measuring point gap, basically. The dwell angle is the duration in degrees as which the breaker points are fully closed. This is actually a more accurate way of setting point gap. So it actually uses a meter that's connected to the ignition coil. I've also seen something where you can pull the distributor out and you kind of set it on a gauge. That's a different thing altogether. It goes for an old Mercury outboard from the late 50s. Anyway, so if your dwell angle is too small, your point gap is too large. If your dwell angle is too big, your point gap is too small. So, as you can see by this diagram here, the dwell angle is the length of time, or the angle that the distributor turns where the points remain closed. So these are types of dwell meters. These actually hook up to the coil, and they'll read as the engine's running. And if you need to adjust, you can adjust the point gap and try again. It's kind of a guess and check method. So, since we kind of got tired of replacing the points and condenser all the time and having all those issues, they went to an electronic trigger later on. Now, the electronic trigger takes the place of the points and condenser. It actually uses a solid-state transistor-driven system that to basically open and close the primary circuit of the ignition coil. There are no moving parts in an electronic trigger that wear out. Your distributor cap and rotor will still wear out, but there's no points and condenser you have to replace. Now, once set, the ignition timing will not change, which is definitely a positive thing, because as the point gap changes, the ignition timing will tend to wander. So this is essentially a Pertronix magnetic trigger kit, probably for a small block Chevy once again. These are really plentiful, easy to install. So we have a magnetic wheel which takes the place of the cam, and we have the little module that takes basically the signal from the magnetic wheel and transfers it into an on-off signal that the coil can use. So this works basically by using a magnetic pickup, which is the ignition module, and a magnetic wheel that is mounted on the distributor shaft, and it spins with engine rotation. The pickup senses the magnet and controls the coil accordingly. The next type is a Hall effect trigger, which is kind of similar but kind of different to a magnetic trigger. So this thing you're looking at is a shutter wheel for a Hall effect. So the Hall effect trigger, we have an ignition module and we have a magnet on the other side. And the magnetic pickup is kind of mounted to the ignition module. The ignition module translates the signal from the magnetic pickup. So in the on configuration, the magnet has a clear path to the pickup, resulting in an on signal. When the shutter wheel comes around and it blocks the magnet from the pickup, this results in an off signal. So for an optical trigger, it's kind of similar to a Hall effect, but instead of using a magnet, it actually uses an LED. So we have our trigger wheel with slots cut in it that let the light pass through. We have an ignition module that connects to the coil, and the trigger wheel takes the place of the cam on the distributor shaft and it points at condenser ignition. So we're kind of looking at a side view here. So we have our ignition module, we have an LED underneath, and we have an optical pickup. When the optical pickup can see the light from the LED, it excites the optical pickup, which tells the ignition module basically that it receives an on signal. And the ignition module will control the coil accordingly. So, and we have our trigger wheel, can't forget about that. So when there's no slot above the LED, the optical pickup sees an off signal and the ignition module controls the coil accordingly. When the slot passes over the LED, the pickup sees the light and triggers an on signal, which again goes to the ignition module and translates to the driver for the coil. Just because the optical pickup is on or off doesn't mean that the coil is as well. The ignition module is able to translate the signal from the optical pickup into a usable signal that the coil can use to fire the ignition. So now that we understand the principles of a distributor and points and condenser style system, we're going to talk about the Magneto ignition. Now this is a Vertex Magneto. This is kind of old school and you really won't see this much at all except for aviation applications, really old like restoration, period correct restoration setups, and racing is another big one. Now the Magneto is basically purely mechanical, and the advantage to a Magneto is that it does not require an external power source to run. So back in the days before electric start, when you basically had to use a hand crank, that's how it produced the spark. You didn't need an external power source. Again, this is good for race vehicles that require an external source to start the engine. I see it very popular in dirt track sprint cars, and also a similar setup in drag cars and stuff like that that don't have a battery or an electrical system. The only problem is this provides poor starting and low speed operation because you need to spin this Magneto up fast enough to produce enough power to create a decent enough spark to get this thing to fire. It's also more more costly than a standard distributor ignition system. So this is basically how it works. I will pause for a little bit for you to read the diagram a little bit, but basically what this is it has a cam that rides, that opens the breaker points, and this cam is basically, this whole thing is connected in one big long setup through the distributor shaft into the rotor. The diagram's not the best, but basically what this does is this is a DC generator almost. And this basically has the coil primary and the secondary wound together. So as the breaker points open, again, magnetic field collapses, fires the coil, which goes up the rotor and out to one of the spark plugs. But the electricity, instead of being generated by the battery, is actually generated by this generator setup here, this rotating magnet in a coil. Again, the capacitor, same thing. The capacitor is basically your condenser, and your ignition switch. In this case, this system actually works by opening the ignition circuit, which allows the whole system to generate electricity. When you close that ignition switch, you're grounding out your points, basically dropping your magnetic field and no spark occurs. This is kind of how a lawnmower engine works in the same principle, except the rotating magnets on the flywheel. By grounding out the ignition system, it stops the engine from running. So, now that we've kind of done our old school stuff here, we're going to talk about distributorless ignition. So, the advantages to a distributorless ignition is there are no moving parts. You get a lot higher voltage than a distributor ignition system because the coils can charge a lot longer versus, you know, having one coil per cylinder or one coil for every 2 cylinders can charge 4 to 8 times as long, depending on the application and the number of cylinders. You have very precise timing control because it's all controlled by computers and sensors. So we have two main types. We have our waste spark, which is kind of an older style system. You don't usually see that too much on very late model cars. And coil per cylinder or coil on plug. That's the most common that you see nowadays. Waste spark kind of went the way of the dodo in the mid-2000s, but it definitely is an effective system and it works very well. So we're going to talk about waste spark, which is a little bit more complicated than coil on plug. So in order to understand the way a waste spark system works, is we need to look at our four-stroke cycle. So we have our intake, piston comes down, compression piston comes up, power, piston gets forced down by the spark, and exhaust. Piston gets pushed back up, pushes the exhaust out the exhaust valve. So times that we want the ignition to fire is right at the top of the compression stroke. If it fires on the intake stroke, it'll backfire out the intake as the intake valve is open and there's all that nice fuel and air in the intake stream. Obviously we want it to fire at the top of the compression stroke, which drives it down for power. Firing the coil in the middle of the power stroke or in the exhaust stroke does nothing. Now, pay attention to this because this is very important. So we're going back to the crudely drawn diagram again. So what I have is basically a cutaway side view of a four-cylinder engine. The little blue things we're going to assume are the pistons. So we have cylinders 1, 2, 3, and 4. Now the way most four cylinders work, as far as every four-cylinder that I've ever seen, is the two end cylinders are in sync with each other and the two center cylinders are in sync with each other. So in this case, we have number 1 at compression, we have number 4 at exhaust. Both our pistons are up. We have number 2 in the power stroke and number 3 in the intake stroke. Both pistons are down. Now we're going to assume the firing order of this engine is 1, 3, 4, 2. It's the way the majority of four cylinders fire. I think my boat fires in a different order, but that's a two-stroke engine from the 60s or 70s, so that's a different ball game altogether, but the vast majority are 1, 3, 4, 2. So basically cylinder 1 is ready to fire. So the way a waste spark system works is we have, in this case, because it's a four-cylinder, we have two separate coils. One coil is hooked to cylinder 1 spark plug and cylinder 4 spark plug. And coil number 2 is hooked to cylinder 2 spark plug and cylinder 3 spark plug. So basically what happens, because we're ready to fire cylinder 1, is the coil will fire both cylinders 1 and 4 at the same time. But as the coil has to work in a circuit, the spark will actually go down through the electrode this way. This is the way my mouse cursor is going on the compression stroke on number 1, and it'll actually jump the other way from the ground strap up through the tip of the spark plug. So this actually provides a very odd wear pattern on cylinders 4 and 3 in this case. Just the nature of the beast is just the way it works. Because electricity has to flow in a circle, this is the direction it flows. So cylinder 1, the fuel gets ignited on the compression stroke, and because it's called a waste spark, cylinder 4, the spark is just wasted. Now, as the engine goes to the next half rotation, we have cylinders 2 and 3 are up. So cylinder 2 initially had the power stroke and has now come back up on the exhaust stroke, whereas cylinder 3 is ready to fire on our compression stroke. So again, the coil number 2 is going to fire, which cylinder number 2 is wasted because it's on the exhaust stroke, and cylinder number 3 is ignited because it's on the compression stroke. Now we're at our third cycle in our four-stroke cycle, and so now cylinder 4 is now on the compression stroke, and cylinder 1 is now on the exhaust, so when it fires, cylinder number 4 is going to ignite, and cylinder number 1 is wasted. You kind of get the picture, so I don't really need to go on here, but that's the way a waste spark system works. So coil per cylinder ignition, Instead of using one coil for every 2 cylinders, it uses a coil per every cylinder. Figure that was kind of obvious with the name. COP, or coil on plug, is another name for it. There's a few vehicles that don't use the coil directly on the plug. GM comes to my mind with the LS engines. All the coils sit on the valve cover with a short little spark plug wire that goes down to the plug. Don't know why they did that. Personally, it's just a pain in the butt, because when you break a spark plug wire, it costs you that much more. These little coils, this one's actually off of a Ford modular engine. I just picked the stock image off of Google, but I'd know that coil anywhere. These things tend to go out pretty often. They're not the best setup. They're kind of cheaply built. So regardless of whether you're replacing the spark plug wire or not, sometimes you just got to replace these coils. They tend to just commit suicide, and you get a random misfire happening on one cylinder. So this is basically the way it works. So we got our 4-cylinder engine cutaway, but now each cylinder has its own coil, and the coils are controlled specifically by the PCM, both the timing and the order. So now we're going to talk about the humble spark plug. These things really haven't changed much in the last century or so. The principle of use is basically identical. So this is an NGK spark plug, just a brand name. So we have a bunch of different parts of this. So we have the terminal. This is metal. This is what the spark plug wire will contact, or the end of the coil. There's usually a little spring inside the end of the coil that makes contact with the terminal tip. So we got our porcelain insulator, so this prevents any voltage from leaking down to the body of the plug here. We have our ground strap electrode. We have our center insulator, which insulates the center electrode. This is where the magic happens, right there. So the spark plug sits directly in the combustion chamber. It ignites the air and fuel mixture, and the design, like I said, has largely been unchanged for a lot of years. So we basically have a bunch of different spark plug electrode types. Copper was the most common, probably up until about 20 to 25 years ago. Like I said, it's been used in a lot of engines, even up until recent years. Usually small engines, lawnmower engines, stuff like that will still use a copper tip plug. It has very good conductivity compared to anything else, actually one of the best. And it's relatively inexpensive compared to the other ones. But it has a very short lifespan because a copper is not really typically a very robust material. And your typical replacement interval is about 15,000 miles, or about 25,000 kilometers. They need to be replaced pretty frequently. And they're actually very easy to spot due to the broad flat electrode on the tip. So here's an example of a copper tip spark plug. You can see the end is very broad and flat. So in kind of more recent-ish years, we went to a platinum electrode. So, like I said, standard on most vehicles. In more recent years, even a lot of vehicles today are still coming with platinum spark plugs. It's kind of 6 of one, half a dozen of the other with what comes with what. I find a lot of domestic vehicles generally use the platinum ones versus the imports, which go with the iridium, which we'll discuss next. Platinum electrode is more expensive, but it lasts roughly twice as long as a standard plug. So, again, kind of the same bang for the buck as a copper one, but you have to replace it half as often. So if you're doing your own work, it's less of a pain in the neck, and if somebody else is doing your work, it actually saves you a lot of money. So your typical replacement interval is 30,000 miles, or about 50,000 kilometers. And it's got a very pointed tip on the electrode, which requires actually a lower voltage to jump the gap. So in more recent years, and I find a lot of Asian and European imports use these iridium plugs. Iridium has the same pointed tip like a platinum, but it's a very hard material that provides a long, long life, a very high longevity over a platinum and a copper plug. Typical replacement interval can be over 100,000 miles, 160,000 kilometers. My Kia Sorento, 168,000 kilometer replacement interval, which is quite ridiculous. But it does cost substantially more than a copper or platinum plug. So where a copper plug is $3 to $5 and a platinum plug is anywhere from $5 to $7. An iridium plug's usually about $12 to $15 each. So if you're putting a bunch of those iridium plugs in, that gets to be a very costly repair. Also, you never ever gap an iridium spark plug because the metal is easily damaged during the process. So just leave the gap alone if you have an iridium plug. So these are an example of a platinum iridium tip spark plug. They got that pointed tip. The double tip one here on the right kind of has a piece of platinum or iridium molded into the ground electrode. It's supposed to help with wear resistance and performance. You know, I'm not quite sure if it works or not. Never really used it myself, but just something to be aware of. That's something you see on platinum and iridium plugs, is the double tip versus the single tip. Okay, so spark plug gap. So the spark plug gap is the distance between the center electrode and the ground electrode. So we touched on this a little bit during the iridium plugs. Too small of a gap and you're going to have a really hard time igniting the fuel mixture because your spark isn't really exposed as much to the air-fuel mixture. If you have a very large gap, the coils may not be able to supply enough juice, enough voltage for that spark to jump a very large gap. So usually the gap becomes too large when the spark plug's really worn out. The tip's really worn down into the spark plug quite a bit, the electrode tip. Too small of a gap generally comes from accidentally dropping it or something like that. It usually doesn't occur from just coming right out of the box. So, like I said, spark plug gap is the distance between the center electrode and the ground electrode. You can check it with a feeler gauge if you want. You know, if you have older plugs, you might want to tighten the gap up a bit. Again, don't do that with an iridium plug, but that is one way to kind of extend your spark plug life a little bit. So the next thing about spark plugs is the heat range. So the heat range of a spark plug is its ability for the spark plug to actually dissipate the heat from the combustion chamber from the insulator tip. So basically, as the fuel burns, the insulator tip heats up. And the heat range is its ability to dissipate that heat from the tip into the surrounding area of the cylinder head. So basically, the longer the insulator is around the center electrode, the quote-unquote hotter the plug is. And this is due to the fact that the heat has to travel further to get into the casting of the cylinder head to be conducted away. So if you have too hot of a spark plug, the insulator will overheat and degrade very quickly. It can actually cause detonation or spark knock, which is a totally different lecture altogether. But because that insulator tip is glowing really hot, it serves almost as a glow plug. So when the fuel comes in the intake stroke, it can actually ignite it if it's glowing hot enough. An overheated spark plug will have a white colored electrode. Almost looks like it's sprinkled with pepper a little bit. So a spark plug that is too cold will actually result in rapid fouling. Fouling is when carbon deposits accumulate on the electrode and kind of prevent the spark from reaching the rest of the air-fuel mixture. And the reason for this is because the spark plug actually doesn't get hot enough to burn off the deposits. So this is the difference between a hot plug and a cold plug. You can see the hot plug's got a much longer insulator cone on here, so the heat has to travel further up and out into the cylinder head surrounding it, versus the cold plug, which has a lot more surface area to the spark plug body. So the spark plug reach is another important thing. So the reach is the distance between the sealing surface of the spark plug and the base, kind of where the ground electrode sits and is attached to, is considered the base. It determines actually how far into the cylinder head the electrode will sit. So if you have a very short reach, basically the spark plug tip will be recessed inside the spark plug hole, and it'll have a hard time igniting the fuel mixture. And because of this, because it's kind of shaded, it will accumulate the deposits inside the plug very quickly because the heat can't really reach it to burn it off. Too long of a reach and the spark plug tip will sit really far into the combustion chamber, and that will have actually spark deposits forming around the threads if the engine happens to run long enough for that to happen. Because of this, it'll actually quickly overheat the ground electrode, because if the threads sit too far out, there's nothing for it to conduct the heat into the surrounding area. So your ground electrode will overheat very quickly and most likely melt. And what will most likely happen if your reach is too long is it will come in contact with the piston. So as you can see here, we have our spark plug reach. So, it's too short, it's incorrect, it's way up inside the hole. Correct is where the base is basically level with the inside of the chamber. And too long, and you're going to get deposits around the threads. Like I said, if it even runs, most likely what's going to happen is your piston's going to come up and bash the spark plug. So spark plug sealing is kind of the last variation here. Seal on the spark plug prevents any kind of combustion pressures from leaking out of the spark plug. So kind of around the threads and that kind of thing. So the combustion pressures can actually leak through the threads if you don't have a way of sealing them. So we basically have two types of seal. We have a taper seat and we have a sealing washer. So this is an example of a taper seat spark plug. You can see there's a taper on the seat of the spark plug. This kind of presses up against the head and seals it. This is kind of an old school method of doing it. Again, back in the days of the old small block V8s, big block V8s, you don't see this too much anymore. You still do, but like I said, it's not as common. And the last one is the sealing washer spark plug. So this guy here has this crush washer. So when you thread this guy in, and it bottoms all the way out against the sealing washer, you want to turn this an extra 2/3 of a turn to actually crush that washer down. And that provides the sealing. They don't really like it when you remove it and install it too many times because you can't really crush that washer anymore and you're going to get some compression leakage going on. For a tapered seal, you only want to turn it about a 1/16 of a turn. You don't want to over tighten it. There's nothing to crush on those. And one other thing with any kind of variations on spark plugs, some of these have multiple ground straps. A lot of the German vehicles do that. I don't really understand why. Some people believe it'll blow the spark right through all the different prongs. To each their own. Doesn't bother me how many prongs my spark plug has as long as it works. So now we're kind of done spark plugs. We're going to kind of get into the heart and soul of the ignition here, which is the timing. Timing's very, very important when it comes to ignition because we want to make sure it ignites the fuel at the correct time. So we need precise ignition timing in order to burn that fuel mixture efficiently. So basically, as you're burning the fuel mixture, the gases expand. It produces a downward force which drives the pistons. So if your ignition timing is off one way or another, it's not going to efficiently push the piston down. So the ignition timing is actually measured in the degrees of crankshaft rotation. So if you have a 0-degree ignition timing, it means that the spark occurs with the piston exactly at top dead center, so right at the top of the stroke. So the piston does not move any higher from that point. 5 degrees BTDC means before top dead center, and that means that the spark occurs with the crankshaft 5 degrees before top dead center. 5 degrees after top dead center means that the spark occurs 5 degrees after top dead center. So the piston's already passed its highest point and started on its way down, and the ignition fires. Versus before top dead center, the ignition fires slightly before the pistons reach the top of its travel. So the earlier the ignition timing event occurs, so the earlier the spark occurs, the timing is considered more advanced. And as it occurs later, the timing is more retarded. So advancing the ignition timing does increase horsepower to some degree. So in this little diagram here, we have the crankshaft 6 degrees before top dead center, so that's considered 6 degrees advanced. Now this one here is exactly at top dead center, again piston at the highest point in its travel. And if the spark is occurring with the piston going downward a little bit, in this case we are 6 degrees of crank rotation past top dead center. If the ignition fires at that point, that's considered 6 degrees of retard. So why do we need ignition timing? Well, too much timing will cause detonation. So basically the fuel kind of exploding almost rather than burning controllably. And detonation can break pistons. It can do all kinds of bad things. It almost sounds like a diesel-like knock. You can kind of hear it. Detonation's very, very bad. Too much retard actually stifles the engine power and fuel economy and actually gives you poor drivability. So in order to burn the air-fuel mixture at the perfect time, the most downward force on the piston, we need to make sure our timing is precise and at the proper time. So the spark usually occurs slightly before top dead center because the fuel needs time to fully combust as the cylinder passes top dead center. So the fuel actually has a burn time. So by starting it early, you're kind of giving the burn a bit of a head start. So your fuel burn rate actually does not change. As engine speed increases, your rate of fuel burn stays the same. So as engine RPM increases, though, the piston spends less time at top dead center. So basically, by advancing the timing, we're giving the fuel burn a bit of a head start before the piston hits top dead center. So as a result, the spark must occur earlier in order to produce the optimum downward force on the piston as the engine RPM increases, because again, we're spending less time at top dead center, so there's less time for that combustion to occur. So your ignition timing at idle is called base timing. So a lot of distributor ignition systems, when you set timing using a timing light, that's known as base timing. Now we're not going to kind of go into setting timing, but we're going to go over all the terms and how it all works. So our maximum timing advance, so when you rev the engine all the way and it hits the very highest timing point that you can get, that's called total timing. Your total timing is equal to your base timing plus the total amount of advance. So if I have 5 degrees of base timing and 15 degrees of total advance, my total timing is going to be 20 degrees. This is not any specific application, that's just an example. So in electronic systems, it is controlled by the engine powertrain control module, or at least a standalone ignition module, for distributor systems, and usually distributorless systems, and it usually uses a pre-programmed ignition timing map. In order to change this, you would have to go in and change the timing map, which is generally done with one of those power programmers, stuff like that will change your ignition timing map. So EFI engines with distributor ignitions also have the ignition timing controlled by the PCM. So what the PCM does is it's able to modify the signal sent to the coil from the trigger in order to more precisely control the spark timing. And a lot of electronic distributors that are aftermarket do have a microcontroller built into the ignition. So rather than using the old school advanced weights and stuff like that, which we're going to get into, you're able to control the timing curve just by adjusting a screw. And so basically the way this works is the distributor rotor has a very wide tip, which allows the spark to travel from the rotor to the terminal for a longer duration. So basically the tip of the rotor is pointing at the terminal for a longer rotational time than basically a standard rotor. And so what this does is this allows the PCM to control exactly when the spark is sent to the cylinder, even if the rotor isn't pointed directly at the terminal in the distributor cap. So as you can see in the image, at this point the tip of the rotor is very wide, so the ignition can fire any time between here and here, and that's what the PCM controls. So non-electronic timing advance. Now, back in the days before computers, now they still make these, again, in aftermarket distributors, usually for, retro applications. But pre-computer days, we had to get a little creative and figure out how to advance the timing without use of computers. So the quote-unquote old-school way of controlling timing advance was to use what they call a centrifugal weight mechanism, or a mechanical advance, and a vacuum pot, which was our vacuum advance. So as the engine speed increases, with a mechanical advance, there are centrifugal weights that are forced outwards. That rotates the top half of the distributor drive shaft, which actually includes the rotor and the trigger pickup. So it rotates it backward ever so slightly. and that allows the spark to actually occur earlier. So there are actually springs attached to the centrifugal weights that pull the weights back in as the engine speed slows down, and that brings the engine back down to base timing as you approach idle. So this is a centrifugal advance kind of cutaway here. So in this case, we have no advance because our weights are all the way in. Our springs have pulled our weights all the way back. So this is kind of in low RPM. So this advance cam is what rotates when engine RPM increases and these weights pull out. So as the weights pull out, the cam moves. So as you can see here, with our weights fully extended, our advance cam will actually rotate, and that gives us our timing advance. So this is in full advance configuration. So as you can see here, our little arm here is actually resting against the advance cam. That's one way of controlling total timing. I know a lot of the newer MSD distributors have some kind of bushing underneath to control the maximum amount of advance. But that's basically centrifugal advance in a nutshell. So the total amount of advance, like I said, is generally controlled by some kind of bushing or mechanical stop located under the centrifugal advance mechanism. So in an adjustable scenario, say those newer MSD distributors, changing this physical size of the bushing will actually limit how far the weights can travel. So the rate of advance, so how fast the total timing can be achieved, is controlled actually by the spring tension and the advance weights. So if you have a high tension spring, it actually resists the weights moving outward. So that reduces your rate of timing advance. And if you have a heavier weight, that provides more centrifugal force, and that actually increases your timing advance rate. So a faster advance rate will achieve total timing sooner, basically at a lower RPM. And a slower advance rate will achieve total timing up higher in the RPM range. So if you have too high of total timing, it has the same effect as too advanced of base timing. Detonation can occur. Too fast of an advance rate will have the same effect as adding too much timing. Detonation can occur as the timing is too far advanced too early in the RPM range. Again, this kind of has to do with, gearing setups, how heavy your car is, torque converter setups for an automatic, so on and so on. The variables are endless with these. You kind of have to tune based on your vehicle. Too slow of an advance rate will basically cause the engine to be sluggish in the lower RPM range, and as it achieves total timing higher up, it'll achieve more power. But your power curve is going to be much shallower lower down in the RPM range. So that was centrifugal advance in a nutshell. Now we're going to go on to the vacuum advance, which basically is this vacuum pot right there. So our vacuum advance advances the ignition timing as the vacuum increases at that diaphragm that I showed before. The intake manifold vacuum is actually highest under light throttle applications, so basically under highway cruising at part throttle. Under light throttle operation, the fuel mixture is lean. When you stomp on it, it richens the fuel mixture. A richer fuel mixture will actually help avoid detonation, but it doesn't run as efficiently. So a lean mixture actually takes longer to burn than a richer fuel mixture. So what the vacuum advance does is it advances the timing during high manifold vacuum to actually start the fuel burn earlier, and that again maximizes your downward force exerted on the piston by the fuel burning. This increases your efficiency substantially under light cruising load. So the higher your manifold vacuum, the more timing advance is provided. So if you floor it, your vacuum will drop to zero as your throttle plates open fully. Again, manifold vacuum, fuel system, stuff like that, that'll be a separate lecture for another day. But when the vacuum drops to zero, the vacuum advance operation ceases. So there's no advance provided by the vacuum advance. The vacuum advance does not operate under full throttle. And the vacuum advance also works independently of the centrifugal advance. So under full throttle, the only timing advance that occurs is the mechanical or centrifugal advance. Under high vacuum, the engine's actually not in danger of detonation, even with a high timing advance, because the engine's under light load. Your high load with too much timing advance is going to cause detonation. So your vacuum advance isn't really necessary. You don't really see it in racing applications, marine applications, stuff like that. But because in racing applications, marine applications, stuff like that, the engine's always usually operated under full load most of the time. So making vacuum advance essentially useless. But in an engine that's doing a lot of highway cruising, stuff like that, vacuum advance actually increases your fuel efficiency and your engine efficiency substantially. So I really appreciate you guys sticking with me through this entire thing. Thank you so much for watching. I hope you learned a lot. I really enjoyed doing this. It took me weeks to actually drop all this PowerPoint stuff. So if you like it, please give it a thumbs up. I worked really, really hard on this, and I hope that the information was helpful to you. So that's basically ignition systems, kind of a broader look at it. You can kind of get more into tuning in a different lecture and stuff like that, but this was basically a little bit more of a basic look at it. So you can follow me on social media. We have Facebook, facebook.com/6SpeedDakota. If you have any questions or anything like that, feel free to send me a message there. It goes right to my phone, so I can generally answer pretty quickly. Twitter, and I am on Instagram as well. So just random pictures I like to post of things, usually cars and boats related, and some stuff about my personal life here and there, and always here on YouTube. So thank you so much for watching once again, and take it easy, everyone.